All right, today we're going to talk about waves. Okay, this is chapter 10. I have your vocab yesterday. Don't forget you got a vocab quiz on Friday. Okay, this is review. This is review for our next unit, really sound and light. Y'all learned this. I'm not seventh grade. Talking about waves, maybe. Okay. They've switched up the curriculum in middle school, so I'm not really sure where. So we're going to talk about waves. A wave is defined as a repeating disturbance or movement that transfers energy through matter or space. Okay, that's what a wave is. Waves move energy. Waves do not move matter. Waves only move energy, transfer energy. Okay, they do not move matter. The biggest example of this is a buoy. Everybody know what a buoy is? A buoy.
Yeah, I heard them.
It's a thing in the river or a lake that kind of marks, kind of marks like on the road, like in the river. There's a buoy on each part of the middle of the river that marks the deep channel of the river. Okay. You also see buoys in lakes where we slow down, things like that. Most buoys are not attached to anything. Okay. Most buoys are not attached. Does the buoy ever move? When a wave hits them, no. Okay, instead they just bob up and down, don't they? Okay, so waves transfer energy. The example of this, but there also is a rock in a pond. We've all done this. We've thrown a rock in a pond. We've seen the waves. We've seen the ripples or the waves go out. The bigger the rock, what happens to the ripples? The bigger the rock, what happens to the ripples? What? The bigger the ripples, correct? The bigger the ripples, the further they go, correct? So that's what it said. The bigger the vibration, that's the biggest thing to take out. Another thing to take out of this is all waves are produced by something that vibrates, whether it be a water wave, whether it be a wave, a sound wave. I want you to say that Kentucky is 2 and 6, and I want you to put your fingers right here over your voice box. I only heard one person do it. Can you feel your voice box vibrating? Okay. Kentucky. So that is a vibration. That's how people that like smoke too much. You've all seen the commercials. The guy's got the hole in his throat, and he's got that little thing that he sticks to it to make himself be able to talk. All that's doing is reading the vibrations. Okay, that's reading the vibration. That's why when your tonsils are inflamed or something like have a cold, your voice changes, doesn't it? Yeah. Because your vibrations are changing. We're going to get a lot more in depth into that, talking about sound in next unit, okay? But a wave is a repeating disturbance. They transfer energy, and they are produced by something that vibrates. A mechanical wave is something that requires a medium. I think a lot of us probably missed this on our vocab yesterday. Kind of problem with it. A medium, what we define in science as a medium, is the material through which a wave travels, okay? Material through which a wave travels. It can be a solid, liquid, or gas, or combination, okay? Right now, the medium that my sound wave is traveling through is air, isn't it? Yes, no, maybe so? Okay, so traveling through there. You can also travel through a liquid or a gas. Which one will it travel the fastest in? A sound wave. Well, think about this. I can tell you this: a sound wave is a mechanical wave. Okay, it needs a medium. So which thing has the most matter? That's the most densely packed: solid, liquid, or gas? Solid. So it actually travels the fastest in a solid. I don't know if I'm sure most of us done this when we were little kids. You got the 2 tin cans, the string in between it, and you tie it and you whisper something in it. You put the other one in your ear. Have y'all done that? And you hear what you have to say. Okay, that's to travel into a solid. Anyone ever heard a gunshot underwater? And you've been underwater with it?
GTA?
On GTA?
You can't even what?
You can shoot a gun underwater.
Not on GTA?
No, maybe not on GTA, but in real life you can.
In real life,
You can shoot a gun underwater. Well, what's going to happen to you if you're underwater with it? It's going to blow your eardrums. Mm-hmm. Yep. It'll blow your eardrums and be too loud. Okay. So yes, that's something that would happen because that sound wave is going to travel faster. So if it's going to travel faster, it's not going to lose much energy when it gets to your ears. There are two types of mechanical waves: transverse and compressional. Okay. A compression wave, I told you this yesterday, also can be called a longitudinal wave. Okay. Longitudinal wave. It kind of goes both ways, depending on your book uses compressional. Other things typically use longitudinal. Transverse waves, this is the definition of a transverse wave, is the matter in the medium that moves back and forth at right angles to the direction that a wave travels, okay? So it moves back and forth at a direction. This is like shaking a rope up and down, okay? If you shake a rope up and down, okay? That is a transverse wave. That's a transverse wave. A water wave, moves horizontally, but the water moves up and down. So water waves are not purely transverse waves, but they do have some transverse wave properties, okay? They do have some transverse wave properties. We'll talk more about these in a little bit. A compressional wave is a very similar definition to a transverse wave, okay? A compressional wave tells you that matter in the medium moves back and forth along the same direction that the wave travels. Notice the difference between a transverse wave. The transverse wave moves at right angles, doesn't it? The compressional wave moves in the same direction, okay? A spring is what a compressional wave looks like. And I've got some pictures here in a little bit, in a few minutes. But if you think of a spring, that is what a compressional wave looks like. Sound waves are compressional waves, okay? Sound waves are compressional waves. Other types of waves are seismic waves. What produces a seismic wave? What? A what? I didn't hear what you said. Understand what you said. An earthquake produces seismic wave. A seismologist, person who studies earthquakes, okay? So a seismic wave is produced by an earthquake. It's a combination of transverse and compressional waves. Objects absorb, when they absorb these waves, they shake. That's why the bigger the earthquake, the more they shake. I can tell you one time when, I think y'all are probably too little. How old were y'all when they blew the levee? Y'all remember that? Yeah, they blew the levee. No, out there by Cairo. They wanted to save Cairo. Well, maybe it's my first year teaching, so probably 10 years ago, so y'all probably 5 or 6.
No, I was 8.
But they blew the levee, and because the river was getting too high, and they put it in the spillway. And actually, they actually created some seismic waves. The waves had so much energy when they blew the levee from the dynamite and the stuff they used that it actually destroyed some houses in Wyatt. Okay, because Wyatt was the closest town. I know somebody that completely blew their front door off of their house. I remember watching this on TV, okay, when they blew the levee. I remember watching it on TV, and you watch the explosion live on TV, and about 15 seconds later, my house in Charleston shook, okay? That'd be a seismic, that's a wave. That wave carries the energy that created a lot of energy. It took a lot of energy to blow the levee, and it traveled through the Earth's crust to there. It actually did register as an earthquake in some areas. They do that. Properties of waves. Waves differ in the amount of energy they carry, okay? Transverse waves and compressional waves have different properties. Transverse waves have crests. They're the highest point of a transverse wave. Troughs, troughs are low, the lowest point of a transverse wave. Compressional waves do not have crest and troughs. Instead, they have coiled regions, which are called compressions, and then the less dense regions, which are called rarefactions. I think of rarefactions as the less is rare. Wavelength, frequency, and period are other things we use to measure these, okay? Wavelength is defined as the distance on one point on a wave, another point just like it. Typically, in a transverse wave, we're talking people either measure crest to crest or trough to trough. On a compressional wave, the 2 points of the wave are, the 2 parts of the wave are compressions and rarefactions. So wavelength would be crest to crest or trough to, compression to compression or rarefaction to rarefaction. Frequency. Who thinks frequency is important? Okay, well, how so do you? Frequency is the number of wavelengths that pass through a given point in a second. Who listens to the radio? What's your favorite radio station? 96.5. 96.5. Anybody else got a different radio station? There's no another radio station? 95.6. Those are, I don't think we actually use 95.6. We typically don't use even numbers. Those are actually frequencies, okay? Those are frequencies, the radio frequencies. Now, all y'all gave me FM radio frequencies, okay? Whether it be 102.9, I like to listen to 97.9. That's where the Cardinals are on. 93.3. Those are different radio frequencies, okay? Can you be we use FM radio frequencies, don't we? If you go to the city, what do they use? AM radio frequencies typically, okay? FM radio frequencies around here you can go a long way. Where's 96.5 based on? Masco or nose? Cape, okay? And you can be, I don't know how far down south or, east or west you can go. We're very flat, so it can make it very far. But can you be in, say, Colorado and listen to 96.5 in Cape?
No, they still be here.
What I'm saying is that frequency doesn't make it that far, does it? Because that's an FM frequency. FM frequencies have very short wavelengths. Okay, we're talking about this. We're talking about this in diffraction. Okay, if you want to go to however, AM radio stations have very large wavelengths. Okay, have a very large wavelength. You can actually, if the weather's right, you can listen to 1120. That's what the Cardinals are on AM in St. Louis. You can listen to that in Colorado. If the weather's right, if there's not storming, anything like that. So the AM things can, we don't use them around here, but they do go very far away. Now let me ask you, 96.5, does it work everywhere in Charleston? It does? I know, sometimes you can weather, things like that. You want to go with the four-way stop or by the focus bank and stuff like that, by tall buildings, it can't diffract around it. We're going to talk about that again tomorrow.
No, I never.
But that is, real life use of frequency. Okay, that's a real life use of frequency. Even satellite radio uses waves, so there are different frequencies. I don't know what the satellite frequencies are that pick it up. And they're expressed in hertz is the units of frequency. Period. Not a lot to add to this. The amount of time it takes one wavelength to pass a point. Okay. Amplitude. Amplitude is the maximum distance that a wave can travel from its rest position. There's a couple typos on there. Rest position. But here's the second thing is the biggest thing to take out of this. On this one with amplitude. The greater the amplitude, the more energy. The greater the amplitude, the more energy. We know this if you think about a surfer. Does a surfer want to ride a big wave or a small wave? A big wave. Because it has the greater the bigger it is, the more amplitude it has, and has more energy for him to travel. Okay, so amplitude. In a transverse wave, the amplitude is from rest position to crest or rest position to trough. In a compressional wave, you look at how dense the rarefactions and compressions are. The more dense the compressions, the greater the amplitude. The less dense the rarefaction, the greater the amplitude. So here is so the top one is a transverse wave. You can see wavelength is from crest to crest. Okay, or I can say it's also trough to trough. Here's a crest, here's a crest, here's a trough, here's a trough. Amplitude is from rest position to crest. Okay, rest position to crest, or probably rest position to crest, or rest position to trough. Okay, we're going to play around tomorrow, messing with some waves and things like that. Here's a compressional wave. Remember, compressional wave is sound waves. Looks like a spring. Okay, you'll notice like A, C, E. See how tight they are together? Those are called the compressions. Okay, and then D, B, and F. They're a little bit more spread out. Those are your rarefactions. And that's where we're going to end the day. Does anybody have any questions for me? Or do you have a worksheet? You have a worksheet that goes on this? And it is due at the end of the day